Here we go, exponential growth, day 2. What we're talking about today is applications of exponential growth. Excuse me, I'll be right back. Okay, let's get this out of the way. You are?
Cody Thomas.
Yes, he had to have that on there. Congratulations. Here we go. When his kids are in my class in 20 years, we'll make fun of them. All right. So 8.1 is exponential growth applications. How does this work? How do these happen when I'm talking about exponential growth? How does the word problem sound and what do they look like? Here's the first example. You're given $200 to invest in an account that earns 5% interest. How much money will you have after 1 year, 2 years, 3 years? Remember, the way that this is talking about, when they say 5% interest, that means it's compounded once a year. So get out your calculators. Yes, I have a class including Cody Thomas, the guy with 2 names. I don't know why he has 2 first names, but that's who he is. So here we go. The one thing that's not on this chart that you need to understand that's hidden is there should be a column that says year 0. And the amount of money that I start in year 0 is $200. So after 1 year, I'm going to have 5% interest. Well, with your handy-dandy calculators out there, what is 5% of $2? If I take 200 and I multiply by 0.05, what do you get? $10. So therefore, after 1 year, I have $210. Now the way that this works, the way compounding works, is now for my second year, I want 5% of 210. So I'm going to take 210 and multiply that by 5%. And what do I get? $10.5 for a grand total of $220.50. I can continue this. After my third year, I can take that 220, multiply that by 0.05, which gives me a grand total of $231.50, we'll round up to 53 cents. What happens here? We're not just adding $10 every year. We're adding more than just the 5% because it's compounded. I'm putting percentage off the money I've already earned. So let's look what this looks like. Just like on yesterday, growth rate and growth factor are words I'm going to be using and talking about, and I want you to kind of figure out what the growth rate and growth factor are. For example, the growth factor for this is 1.05. The growth rate for this is 5%. And at the end of this, we'll talk about what those definitions are, but I want you to think of those 2 words, growth rate and growth factor, and how they might be different. Next slide. In 1990, the cost of tuition at Colorado State University was $4,300. During the next 8 years, the tuition rose 4% each year. Write a model that gives the tuition Y in dollars T years after 1990. Okay, so let's look at this. In 1990, what year is that? That's year 0. So I'm starting out with $4,300. Okay. What am I going to multiply that by? Yes, sir. 0.04 is going to give me my percentage increase. I agree with that. I want that in my problem. I want 0.04 as part of my problem, but I left a blank. Because what is 4% of $4,300? Calculator. Quickly. 172. So does that mean in the second year that I just pay $172? I have to pay $172 on top of the 4,300. So I need to have a number 1 here. That number 1 not only gives me the original amount, and I add that to the percentage of increase. And then I'm going to have a T. The T represents the time, the number of years, the number of times I'm going to compound this because it increases every year. So this is my equation. You can simplify it. Excuse me. To that. But those are the different parts. That is my model. Let's go ahead and graph this. Now I'm going to pull out my handy dandy calculator. Pause for station identification. So now that I have my my calculator, and yes, Mr. Cody does have to say something else so that we can hear him. Say hi, Miss Morgan. Congratulations. Here we go. What I want to do is hit y equals in my calculator and plug this in. So I want to plug in 4,300 times 1.04 to the t power. Now technically I have to put to the x power because the calculator doesn't have the variable t. The next thing I need to do is I need to pick a window that's going to work with this information. Now the number of years, it's right now it's the year 2012, which is 20 some odd years after 1990. So let's go ahead and have my x's go from 0 to 30. Not 330, let's go 30. Let's have our y's. My y's need to have 4,300 in it. I personally like to have the y-axis, the x-axis is part of it. So I do start with 0. I need to go up, let's go up to $15,000. And let's count by thousands. So when I graph this, this is what my graph looks like. Okay. Now, as a teacher, I can just slide this over here and ta-da, there's my graph. If you're going to graph these points, what would you do? Well, you could hit second graph to go to the table. You wouldn't want negative numbers, but I would go ahead and I could pick points here and I can graph them. And that way I could get a pretty good idea of what the graph looks like. So there's how to get your model. There's how to find your graph. Example 3b. In 1980, about 2,180,000 U.S. workers worked at home. During the next 10 years, the number of workers working at home increased 7%. I need to go back one thing and make a comment. On this problem, you would say the growth factor is 1.04 and the growth rate is 4%. The growth factor would be 1.04. The growth rate would be 4%. So let's go to this new problem. In 1980, about 2,180,000 U.S. workers worked at home. During the next 10 years, the number of workers working at home increased 7% per year. Write a model giving the number W in millions of workers working at home T years after 1980. So again, the setup is the same way. W is equal to something times something to the T power. What do I start with? Do I want to write 2,180,000 up there? Well, I want to write 2.18 because it says I want this to be in millions. So I'm going to write 2.18. Okay? What's my growth rate? 7% is my growth rate. I'm sorry? My growth rate is 7%. So what's my growth factor? 1.07. That's what goes in here. 7% is my growth rate. My growth factor includes that 1.07 as a decimal. Here is my problem. So then I could come down here, 1980, right now, like I said, it was 2012. So this is 32 years. So my x's, again, I'm actually going to fill this out a little more, would go from 0 to, 5, 10, 15, 20, 25, 30, 35. So these are years since 1980. Here, I'm at 2.8 million. So yeah, let's put every 2 as 1 million. So this is 3, 4, 5, 6, 7, 8. So that goes up to 8 million. I might have to change that later. Now I need to say that this is U.S. workers, U.S. workers at home. And then I need to say in millions. And I took the 8 with me. That's all right. And I know that's crooked. Deal with it. So then what does the graph look like? Again, we could kind of figure that. Yes, sir. On a problem like this where I will say, please label your axes, yes, I will mark off. So again, you can use your calculator to set this up. I can come over here. Let's bring it up so I can see my actual problem. I go to y equals. I'm going to plug in 2.18 times 1.07. That's going to be to the x or t power. I need to change my window. My x's on my graph I had going to up to about 40. My y's, I don't need to go anywhere near as high as 15,000. Let's just start with 10. Count that by ones. And so here's what the graph would look like. Again, if I actually want to graph this, now if I'm actually want to look at now in the 30 and 35, is my y high enough? If you, this is going to look weird. If you look over here, I'm not actually hitting my graph. So my y's probably have to change. So let's go back to my window. Instead of 40, let's go ahead and make this 100 and graph. I changed the wrong one. So let's go back. Let's go back. Go back. Thank you. Keep that as 40. But in this, instead of this being 10, let's change this to 50. And that's probably a little high. I probably could have made that also 40, and that would be a good look for us. Okay, so that gives me the data that I can see. So I need to come back over here and multiply everything by 5. So I would have 5, 10, 15, 20, 25, 30, 35, and 40. And my graph would start down here. And it did an arc like that. I could be more specific. I could definitely go to my table and I could actually plot points. I could even hit second window, go to table set, and make this count by 5s, just like my graph does. And I could even plot 0, 2.18, 5, 3, 10, 4.3, 15, 6, and so on, and see where this graph actually goes. I could be a lot more specific when it comes to graphing these. Okay? Questions on graphing this type of a problem? Notice I do want you to use your calculator. It's a nice thing to have and to use. Compound interest. Write this down, please. Make sure you understand what compound interest is and what it does. If you look at this, it's very similar to the equation that I was writing earlier. I was saying y is equal to an original amount times 1 plus r to the t power. This is similar to this, but I've added an extra variable. First of all, A is the amount of money after t years. The P is my principal, my original amount of money. Both of those, neither of those are different. R is the rate of growth. T, I don't have this up here, but T is time in years. And then the new variable, the thing that's different, is N. N is the number of times the account is compounded in 1 year. Everything we've done up to this point, we're compounding at the year. Tuition raises once a year at the beginning of the school year. Here, I can compound things multiple times. I can do it monthly. I can do it weekly. I can do it every 6 months, which is twice a year. I can do this daily, and then we can kind of go from there and look at some more interesting things. But right now, we're just going to be getting familiar with this equation. Excuse me, 1 second. So as people walk in, we're going to have some disturbances. We'll throw some things at them, have a good old time. So here we go. What does this look like? Now, the question that was asked was N. What are you laughing at? I don't want to know. I have a ball to throw at them. You think I'm lying? N. Again, the new thing is N, compounding more than once in a year. The way that banks compound is they compound using something called compounding continuously, which actually is an idea that we get from calculus. We're not going to learn the calculus behind it. We're just going to use different things. So let's look at this. You deposit $1,000 in an account that pays 8% annual interest. Find the balance after 3 years if the interest is compounded with the given frequency. Letter A isn't changing anything from what we've been doing. A is equal to 1,000 times 1 plus my rate, which is 0.08, and I want this for 3 years. Figure out what that amount is for me, please. Plug that into your calculator. Give me a number. We will pause so that you don't have to wait for them to do the work. So I am told that the answer is 1,000. 712. So $1,259.71. If I'm compounding annually, that's how much money I will have after 3 years. Let's compound quarterly. That means after every 3 months. My A is equal to my principal is 1,000. My 1 stays the same, plus 0.08 is now going to be divided by 4. And this is 4 times 3, which we all know is the number 12. So if I go to my calculator, and I wanted to do this in my calculator, I'm going to plug in 1,000. Let's see if I can do it all at once. Parentheses, 1 plus 0.08 divided by 4. Close my parentheses. The calculator will divide before it adds, so that will work. And I want this to the, I hit the wrong button. Let's try this again. 1,000, plus 0.08 divided by 4, since it's compounded quarterly, to the, I'm going to put 12th power. That will give me my final answer. I can do it all at once. I get $1,268.24. So that's $1,268.24. So just by compounding quarterly, I've done nothing extra to my money, but because I compound quarterly, I just made an extra $9. And it had nothing to do with the money. It's just the way that I choose to put the money back into the account. I compounded quarterly. But what if I compounded daily? How many days in a year? Except for this year where we have, how about 366? You said 4. No, I'm hearing things. Okay. My mufflers are getting in the way is what he says. Okay, so A is equal to 1,000 times 1 plus 0.08 divided by daily is 365 days to the 365 times 3 because I'm doing this for 3 years. Again, I bring up my handy dandy calculator. I'm going to bring up the last thing I typed by hitting second enter. I'm going to come through here and I'm going to change the 4 to a 365. I'm going to change 12 to 3. Now, since I'm doing the multiplication here, I'm actually putting parentheses. So I'm going to do 365 times 3. I don't want to know what you're doing back there. Shh. So here we go, one more time. My original amount is 1,000 plus times 1 plus 0.08 is my percent increase. 365 days a year because I'm compounding daily to the 365 times 3. That's the way this equation works because we set for 3 years. And this gives me $1,271.22. So that's $1,271.22. Again, I haven't done anything differently here. The amount of money I put into the bank is exactly the same, but I went from $1,259 to $1,271, a difference of $12. Now, if you're just thinking of $1,000, it's not too bad. But what if you had to pay an extra $12 just because they're compounding daily instead of annually? What if it was more than $1,000? What if you're talking about a house? A house, you're talking about at least $150,000. That's a lot of extra money that gets compounded in there. So, the next thing is our homework. Our homework can be found on page 470 through 472, numbers 43 through 45, 56 through 65, 68, and 69. Have a good day.